So we're shifting gear now. We're on to chapter 5, okay, which is around forces and loads on the tyre, with a little bit of driveline thrown in for good measure, okay. And this should be quite straightforward. It's obviously based upon level 1 and 2 dynamics, okay. It should be quite straightforward just to follow along with what's going on. But we can talk about the forces on a car, talk about static loads, so when the vehicle's not moving, and then dynamic loads when it's accelerating and moving, okay. And then we'll also bring in a bit, like I said, a bit of driveline stuff to do with tractive force and the powertrain relationship between those loads on the car and how they change when you start applying tractive forces to the car. So the forces on the car, what have we got? Well, here's my car, okay, a BMW i8, and it's moving this in that direction, okay, and obviously to provide that movement in that way, you need a tractive force, okay, generated from the engine or the electric motors or whatever is powering the vehicle, okay. There's a tractive force that's going to push the car. Obviously, opposing that motion is a resistive force. Okay, that tractive force has to overcome that resistive force. I don't know why it's not showing up there anymore, but it's showing up here. Okay, and obviously that's in the horizontal direction. You've also got weight and lift forces in the vertical direction. Okay, so you've got the weight, obviously, and a normal force, and ideally those things should match up such that the car doesn't end up flying, okay, or doesn't sink into the ground. But obviously, if you've got equilibrium, then the vehicle will sit on the ground and it's not moving it up or down. But the tractive force, those horizontal forces are what's more interesting here. Okay. So what are the resistive forces made up of? Well, you've got a few different resistive forces. We've got aerodynamic resistance, okay, which I've called FA. Okay, so that's resistive force. As the vehicle moves, it's moving through a fluid, okay, through the air. And obviously that, the factor's got a shape, means that it's going to have some resistance as the vehicle moves. Okay, we'll talk about what that aerodynamic resistance is. It's also got rolling resistance. We just talked about that. Okay, as the tyres roll, they deform. That creates a negative a force that opposes motion. Okay, so that obviously also has an impact. And clearly, if the road is not flat, okay, if it's going up or downhill, then there's going to be some sort of resistance in terms of the road grade. Okay, so how steep the road is. So those are the predominant resistive forces, okay? And then obviously the tractive force, you've got to overcome them. So if you could write an equation, so the resistive forces is FA plus FRR plus FG, so there's your aerodynamic, your raw resistance and your grade forces, okay? That's your total resistive force. And obviously the tractive force minus your resistive force is the sum of the forces, and that equals mass times acceleration, as Newton's second law. Okay? So FT, the tractive force minus the resistive force is going to equal your mass times acceleration. So to work out the acceleration, you take your forces, you divide them by m, and you're going to get x to the log. Okay, which is how fast the vehicle's going to accelerate. Clearly, if you don't want to accelerate, then this thing is 0. Okay, and those things need to match each other. What are those resistive forces actually in sort of apparent? Okay, so obviously up here I've replaced FR with those forces in here, okay? You get that. So what are FA and FRR and FT? Well, here's that vehicle in a wind tunnel, okay, just to show you, okay, and obviously what you can do is you can make lots of measurements, you can look at aerodynamic drag, okay, and how does that build up? Well, about the largest bit is around turbulence of the air as it flows around the vehicle body and behind the vehicle body. Okay. You look at cars with very low coefficients of drag, they're very streamlined, okay, and they've got a either very sharp tail cut off, or they tail off to nothing. If you look at the things like the McLaren Speed Tail, that's got a very long body, very streamlined, and you can see that the back end, it basically is like an aerofoil that comes to a point. Okay, that's not particularly practical for lots of different cars, but like I said, you've got this sort of setup, and that's around trying to deal with this turbulence, which is the biggest component of aerodynamic drag. Okay? The other thing is about friction, air friction over the body. Okay, so if you look at so obviously that makes a difference, the size of the car, the length of the car. But if in a particular example of that, if you look at the TGV in France. Okay, I'll see if I can find it. There was a they did a record attempt, and obviously one of the that's a big electric train, can go very fast. To minimise, it's got two locomotions and then 2 carriages in the middle. And so, like I said, obviously the idea was to minimise the friction drag, because a very long train's going to have a lot of surface area. It's going to have a lot of drag. But this thing got to almost 600 kilometres per hour. Okay. So obviously that's about 12%. Okay, and then obviously there's also got some components on top of there. So you've got radiators and air vents and those sorts of things, and they all add to drag. Okay, and so obviously those if they can close up and that sort of stuff, then you'll get a better efficiency. And you can see that on quite a lot of modern cars, they'll have active vents. So although it's got a grille on the front that looks static, behind the grille there'll often be flaps that will open and close depending on what the engine needs in terms of cooling, that sort of stuff. And the whole idea behind closing them is to reduce the aerodynamic drag when you don't need them. Like I said, there's a very big focus on electric cars, okay, because obviously one of the big things about electric cars is their range, okay. To maximise the range, we will also talk about tyres in a second, but obviously the other thing is looking at aerodynamics. And so you could look at some of the more recent electric cars and things like the Hyundai Ioniq 6. I don't know whether you've seen that, but that looks it's quite an interesting looking car. But the whole idea is around aerodynamic efficiency. The same thing with if you look at the electric Mercedes. So like if I type in the Mercedes EQS, the same profile, yeah. So here's the EQS again. It's all around aerodynamics. That shape is very low drag. And I think the this vehicle and depending on the tyres you get, we're getting to 0.25 drag coefficients and things like that, which is very good for a regular road vehicle. So how do we actually get a value for this? Well, there's a straightforward equation. Okay, so all these things feed into this value CD, which is drag coefficient. Okay, so you take 1/2. Okay, that's obviously 0.5. Rho is the density of your air. That can obviously vary depending on where you are on Earth and how high you are and that sort of stuff, but there's a standard value that we take for density, okay? CD is your drag coefficient. So like I said, a good road car, regular road car is probably about 0.3, 0.35, that sort of thing. Something like those electric cars, we're getting down into the 0.2s, okay? And if you look at high performance cars with aerodynamic devices and stuff, then this value actually grows quite a lot, because those aerodynamic devices, while they give you downforce, create a lot of drag. Okay. But CD, like I said, A is also a big factor. That's the projected frontal area. Okay, so you take a photograph of the car at the front. Okay, and you trace the shape that's looking at you. Okay. So obviously, like I said, I mentioned the tyres being, how big the tyres are having an impact on aerodynamics. Well, wider tyres will give a bigger projected frontal area. Okay, so obviously that's, like I said, the thing that is impacting you. So obviously it's something that's very narrow, okay, like a vehicle with tandem seats perhaps, okay, obviously a much smaller projected frontal area. So often it's this CDA value that's the big factor, the aerodynamic drag, the drag coefficient times by the frontal area, that's the big sort of factor. And then, notice we've got a V in there, how fast you're going, and it's squared. Okay, so you double your speed, your drag's going to go up by 4. Okay, so like I said, vehicle speed is very, very important when it comes to increasing the aerodynamic drag, which is why going from 70 to 80 on a motorway, it switches. That's really weird. That's oh dear, this is not. Why is it doing that? Is it?
Variation.
Yeah.
Okay, so yeah, CDA is the big important, and then your velocity squared. And like I said, if you're doing 70 on the motorway and you go up to 80, you haven't just increased your drag by just over 10%. You've done it by more than 10%, like 20%. Okay. So like I said, although it's not a big difference in speed, it's a big difference in drag forces. Engines working harder, you're using more fuel. Okay. That's what's going on. So as I mentioned, you've got your density of air. Okay. Density of air. You've got your coefficient of drag, your frontal area, and then your velocity. Okay. Squared. What about rolling resistance? Well, I mentioned that, okay? It's from the deformation of the tyre, predominantly, obviously penetration, surface compression, and then slippage and air circulation around the wheel. Obviously, the rim design has quite a big impact. Okay, you've got 6%. That's why often electric cars will have quite different types of wheel designs. Okay, all around trying to minimise that air circulation. So that's why a lot of the Formula 1 cars this year, they've got those wheel covers, and a few years ago they all had wheel covers as well. It's the same thing, trying to minimise the drag around a rolling wheel. Okay. And I mentioned this, I've used slightly different variables here. CIR being the coefficient of rolling resistance. N is your normal force, so vertical load, and that gives you a general rolling resistance called FRR. Okay. Coefficient of rolling resistance, your normal load on the tyre. Okay. And then, an example, the road surface also makes a difference. So it's not just about the tyre, it's about the interaction of the road surface. And so we've got different types of road surfaces here. So concrete or asphalt, we're talking 0.01 or 0.015 as a sort of surface. Okay. Rolled gravel, so compacted gravel down, unpaved roads, and then loose sand. You can see the big difference between concrete and sand. Big, huge difference in terms of rolling resistance. Okay, and like I said, the speed also makes a slight difference. Okay, but often what you do is you assume the constant speed. Okay, so you say basically if the vehicle's moving, then you've got a rolling resistance force, and that rolling resistance force is going to be constant. It starts to be interesting when you're modelling the stuff, because you can get if you say the rolling resistance is constant irrespective of speed, you can actually have your model set up, and when you press go, the thing starts going backwards because the rolling resistance is bigger than all the effective forces. Okay, so you obviously need to be a bit careful about what's happening at very low speeds. What about the grade? Well, here's my car. It's going up a hill. My hill has got an angle of theta. Okay, measured in degrees or radians, okay? And obviously I've got a gravitational force on the vehicle, and that can be decomposed into two components. One in the direction the vehicle's travelling, and one perpendicular to the way the vehicle's travelling. And obviously, using a bit of trigonometry, you can see we've got opposite over hypotenuse here, here, and adjacent over hypotenuse there to give you the sine and the cosine forces. Obviously this bit is the resistive force, okay? The bit that's in the direction of the vehicle travelling, okay? mg sine of theta is going to be trying to pull the car down the hill. So again, that's your resistive force, that's your grade resistance. And that's, like I said, just basic physics. In the direction of travel, the Fg is mg sine of theta, where theta is the angle of the road with respect to the horizontal. So those are the sort of loads on the car. Let's work out what the normal loads are on the wheels, okay? With all these different resistive forces. Okay, so here I've got my vehicle, I've got my centre of gravity, okay, and I've got my wheelbase, which is the length of L, okay, and I've got my distance between the rear axle and the centre of gravity is distance D, and from the front axle to the centre of gravity, I've got distance C. Okay. So C plus D equals L, okay, those two lengths equal the wheelbase. The wheelbase is the distance between the front axis and the back axle. And I've got a height of the centre of gravity above the ground, which I've called h. And then I've got my two normal forces here. Okay, they're perpendicular to the road surface. Okay, and clearly these two forces need to deal with what's going on here. So we're dealing with static loads, not dynamic loads. The vehicle's not moving. Okay, we'll talk about that in a second. But if the vehicle, say, parks on the hill, what are the normal forces on the wheels? Okay, and so we can go through the motion. So if we set that up in the corner, taking moments about the rear tyre. Okay, I should have put some coordinates on here. Okay, we'll take moments around here. So we've got this. We're trying to rotate it this way. We've got the mass. We're trying to rotate it this way. Okay. So you take moments about the rear tyre. NF times load. So yeah, anti-clockwise is positive. Okay. So you've got your NF times by L. This one here times by the length L. Is trying to push it this way. We've got mg/d. Okay, so which is this cosine, this one here, okay, so that's a distance d, trying to rotate it this way, okay, and we've got mgh, which is trying to push this one here, trying to rotate it this way. So you can go through that, and then obviously you can do some manipulation, and you get your value for your normal force at the front by taking moments about the rear contact patch. Okay, and then if you do the same thing for the front contact patch, okay, so again now we're taking moments around here. Okay, you've got your NRL, which is going that way, and then you've got your both of these forces going this way. Okay. So you have the cosine and the sine of these terms. And again, you can rearrange that, solve for NR. You end up with these two equations. So they're quite similar. Instead of D, we've got C's, okay? And instead of a minus, we've got a plus in there. And obviously, if theta is 0, then various things happen. Obviously, cosine of 0 is what? 1, okay? Sine of 0 is 0. So that term disappears, and we end up with just mgd upon L. Okay? With this one, obviously, cosine of 0 is 1, sine of 0 is 0, so we end up with mgc upon L for the rear. Well, that makes sense. Yeah, if you've got front rear distribution, okay, obviously the distance of the centre of gravity, so the percentage, yeah, this C upon L and D upon L, obviously that's going to dictate the distribution. So, let's go through an in-class questions. We've got a car of mass 1,500 kilograms travelling up an incline of 5 degrees at a constant speed, so it's not accelerating. Determine the normal loads on the front and rear axles if its centre of gravity is at a height of 0.6 metres above the road and a distance of 1.2 metres from the front axle. The wheelbase is 2.6 metres. Do you want to see those equations again?
Yes, please.
I'm assuming we're taking gravities now.
Yes, yes.
No, I just want to double check. Sometimes it's like, oh, we're just taking it as 9.8. Yeah, but I had it from my
don't forget, when you're doing this problem, okay, I've given you an angle in degrees. Your calculator may still be set for radians, okay, so make sure you change that. Okay. So here I've got my MATLAB up. I've got, so my mass is 1500 kilograms. Theta is 5 degrees. Okay, I've got my height, my distance C, and my wheelbase L. Okay. Obviously D is going to be L minus C. To get my distance D, and obviously I've got G is 9.81. And I just apply the equations. There's my NF. Okay. And there's my NR. And if I run the code, I take the colons off of here, and it will display the code. So my NF is 7,597.3 newtons, and my NR is 7,062 newtons. Okay, so those are the values. If you want to work them out yourself using, like I said, the code is on MATLAB as well. So what about dynamic loads? What do we mean by dynamic? Well, the vehicle's not only either moving at a constant speed, okay, that's actually the same as static, but this time the vehicle's accelerating. And so there's going to be some more values that we need to worry about. We've got the rolling resistance on the front and the rear. We've got our acceleration, our inertia, okay, and obviously aerodynamic drag as well. And obviously there's going to be tractive forces at the front and the rear. And so by adding those values in, we can actually worry about the moments about the rear contact patch. Okay, so again, we take this moment here, moments around here. Okay, fortunately none of those are impacting this. Okay, the roll resistance, because they're in line with this point. We've got NF going this way. We've got MX going this way as well. We've got MG going this way, and the aerodynamic drag going that way. Okay, so you can put all these things in there. Okay. Sum of all the moments must equal 0. And so you can go through the motions and rearrange to solve for NF. So everything else goes on the other side of the equation, and then you divide it by L. Okay, which is what's going on here. So there's your equation for NF. Okay, you could do the same thing for moments about the front contact patch. Okay, so again, moments around here, none of those take an effect, but this one does, it's going that way. Okay, you've got MX going this way, MG going this way, and FA going this way. So most of them are positive, except for NRL, okay, that's the minus sign. And we can solve for NR, putting everything on the other side, divided by -1, to get them all plus, and then divided by L. And so there's your equation for NR. Okay, now all I'll do is I'll pop those equations on this slide. Okay, so if I go back. So we've got another question, the same problem, same vehicle. Okay, but this time we've got some more complicated equations. And the equations are NF, okay, equals MGD okay, minus MGH sine the theta. Okay, so that's the same. But then we've got our aerodynamic drag, FA, H, minus M, X double dot, H divided by L. And then our rear, There's our two equations. Okay. So if you go into MATLAB, okay, so down here I've added my X double dot term. I've set my aerodynamic drag as 0. So there's my equation from the sheet. So that bit is the same. These two terms are the same. So I've got my minus FA times by H minus MX double dot times by H multiplied by L. Okay, and then so down here it's plus FA times by H plus MX double dot times by H. And if I run that code, if I take oops, down here. If I take the semicolon off there, and run that code. So we get 6,212.7 for the front and 8,446.3 for the rear. Does that make sense?
Yeah.
Okay, the vehicle is obviously on a hill, so there's going to be more weight on the back anyway. Okay, despite the C and the H, but it's accelerating. And what happens when you accelerate? Well, you get a weight transfer to the rear. Okay, which makes sense. Okay, because the thing is accelerating. So obviously the back end is going to have a bigger normal force than the front end. But yeah, so you get obviously that weight transfer to the back. It's going to give you a bigger normal load on the rear axle. So we've got 6,000 and 8,446.3 newtons. Okay, so there's your solutions if you want to work it out yourself. And like I said, that makes sense. We've got a bigger weight we've got weight transfer on the back because we're accelerating. Okay. So when you're accelerating from low speed, from standstill, okay, obviously your aerodynamic drag and your roller resistance and your grade value are 0, okay, because obviously you're at standstill. Okay, so you can take out some of these terms. Okay, we end up with the normal force. You know, obviously that cosine term is 1. That value is 0. That value is 0. You've got mx double dot plus over h times by L. Well, obviously that mgd upon L is your weight on the front. Okay. And then you can work out the normal load at the back. Okay, so again, FA is 0, sine of 0 is 0. So you've got mgc, okay, cosine of 0 is 1, mgc upon L, okay, which is the weight at the rear, and then you've got your mxh at the back. Okay. So you can see that the difference between these loads, okay, is that mx double dot h. That gets added on, and that gets taken away. That gets added on. So that bit is your weight. Is your weight transfer. Yes. The weight, mg. Well, w is m. Okay. No, I'm not giving it specifically to you, but that's mg. Yeah, at the front, and mg at the back. Okay. And that's because you've got d upon l and c upon l. Okay. Yeah. So when you hear somebody talk about weight transfer, okay, under acceleration, that value there is your weight. What is your delta w? Okay. On the back end, when you're accelerating, it gets transferred to the back. Okay. But obviously, if it gets transferred to the back, it's taken away from the front, so you get that. So delta W, okay, is that mx double dot h upon L. Okay, so the higher the centre of gravity from the ground, the more weight transfer there'll be. Okay, so obviously that, and obviously the longer the wheelbase, the less weight transfer will be. Okay, so a long wheelbase car with a low centre of gravity is going to have a lower weight transfer than a high car with a short wheelbase. Okay. Weight transfer due to acceleration. So, another in-class question, number 3. Okay, so we've got a different vehicle here. The loads carried by the front and rear axles of a car with stationary on level ground are 850 kilograms and 950 kilograms respectively. So those are the masses. Obviously, to get the weight, you need to multiply by G, okay, in newtons. Determine the load distribution on the axles when the car is given a forward acceleration of 5 meters per second if the centre of gravity is 0.54 meters above the ground and the wheelbase is 2.8 meters. Okay. What would be the load distribution if the car is given an acceleration of 5 meters per second up an incline of 1 in 12? Okay. So 1 in 12, what I mean by that is that you move along 12 meters horizontally and you go up 1 meter. Okay. So 1 in 12 means. So the equations here are the ones we've used in the previous page. So NF okay, so let's do part A first, okay? So if I go back to MATLAB and I load up.
You know December where COVID was like,
Every day.
I was so ill, like it was so bad. I've never seen myself. And then from there,
Okay, so those are the two values, okay? So basically in the code I've got my mass at the front and my mass at the rear. Okay, so my total mass of the vehicle is obviously 1800 kilograms. Yeah, okay. And my height, my centre of gravity, my acceleration, my wheelbase and G, and I've just got mf times by G, which is NWF. Okay, minus m x double dot times 8 divided by m. Okay, and the same for the back as the plus. Okay, so my weight transfer in the front, so I've got 6,628 for the 6,602.8 for the front, and then 11,055 at the back. So if I go back to my thing, 6,000. Okay, so those are the values for part A, okay? For part B, I need to work out D and C, okay? So we've got, what have we got? We've got MF is 850 kilograms, okay? Which is also equal to D upon L times by M. And so we can rearrange that equation to solve for D. It's going to be MF times by L divided by M. Okay, so that's going to be 850 times by 2.8 divided by 1,800. Okay, and that's 1.322 meters. Okay, and MR is 950. That's going to be C upon L times by M. The C is MR times by L divided by M. Okay, so those are my values for D and C. Okay, so now my equation, because I've got my grade in there as well, I've got mgd times by cosine of theta minus mgh sine of theta, okay, minus mx double dot h all divided by L. Okay. And then for my NR, mgc cosine of theta plus mgh sine of theta plus mx double dot h all divided by L. So the equations we had before. So again, if I go on the angle, okay, we've got 1 in 12, 1 in 12. So theta is going to be the inverse tangent of opposite over adjacent. So 1 divided by 12, and that comes out to be 4.76 degrees. Okay, so let's put that in there. Let's go to MATLAB. So let's do that. So that was we'll get theta first. So we'll say theta is the inverse tangent in degrees 12 divided by 1 divided by 12. Okay. And then we said NF. Oh yeah, when D was MF times by L divided by M, and C was MR times by L divided by M. And then we said NF M times G times D times cosine of theta minus M times G times H times sine of theta, and then minus M times X double dot times H, and that's all divided by L. I think that's right. Let's have a quick check. mgd cosine of theta minus mgh sine of theta minus mx double dot times by h. mgd cosine of theta, mgh sine of theta. Yep, okay, so that's fine. And then nr is very similar. Oops. But we've got plus in here and plus at the end. Plus there. We've got plus at the end as well. So, and we've also got mgc. So if I run that, so 2000. No, that's not quite right. MG minus minus minus. Okay. M times G times D cosine theta. Oh, cosine D. Don't fall into the trap where you've where your degrees and radians. Naughty. Right, let's try again. So 6,291 newtons. Okay, and then NR is 11,306. So although we're going up a hill, there's going to be more weight transfer to the back, but it's still not enough for it to do really. It's still got 6,000 newtons on the front axle. So if I go back to the presentation, we've got and that's 11,306. Okay, here's your answers for this second part of this problem. Right, I think actually what I'll do, because we've not quite finished the presentation, we'll talk about drivetrain next week.